Good afternoon, everyone. I'm Judy Geller, Director of MetalCon, and I am delighted to welcome you to MetalCon Live. Today's topic, AISI S250, North American Standard for Thermal Transmittance of Building Envelopes with Cold Form Steel Framing. It's presented by Jonathan Humble, Regional Director of Construction Codes and Standards from American Iron and Steel. Before I hand things over to Jonathan, I just wanted to share with you that MetalCon is coming up. It's hard to believe that we're less than 5 weeks away from the show, and we hope you'll be able to join us in Indianapolis for an exciting event this October 12th through the 14th. This year's show will feature more than 200 exhibitors, more than 40 education sessions. It's got pre-show workshops. It's got a new metal building marketplace, an education center dedicated to sustainability topics. It has the Architects Experience, our show within a show for architects, designers, engineers, and specifiers. I can't possibly list everything that's going on at the show, but I do hope that you can join us. And this year, be sure to bring your future leaders. We've developed special programming and networking for your up-and-comers and rising stars. It's going to be great for them. Finally, MetalCon 2022, the next MetalCon Live, please mark your calendars for the next MetalCon Live on September 21st, when the Metal Construction Association presents Insulated Metal Panels Installation, Factors that Influence GERT Spacing. Finally, if you need technical help, be sure to reach out to MetalCon support in the chat box, and don't forget to complete the post-show webinar survey so you can earn your AIL learning units for today's session. That's all I have, and now I'm going to hand things off to Jonathan. Jonathan, take it away.
Well, thank you very much. I'm Jonathan Humble. I'm a Regional Director of Construction Codes and Standards for the American Iron and Steel Institute. Today we'll be discussing AISI's S250 standard, and that standard is brand new out of the box. It was developed, which I'll go through its history, to try and standardize how to calculate the thermal resistance of assemblies such as walls, roofs, and floors, thermal transmittance, in order to comply with the energy codes that are adopted in various states or jurisdictions even outside of North America. Now well, we've already got a technical difficulty. Here we go. Just as a notice, we have to note that the
Oh, I'm so sorry, Jonathan, but it doesn't seem like we can see your screen.
Really? Okay, we'll try that again. Here we go. Slide number 2. Does everybody see the copyright notice? Excellent.
Yes, we can.
This is all copyrighted material. As a result, please don't reproduce, distribute it. However, you can ask us for information as necessary. We do have a hotline for AISI. Objectives today: to provide a brief history of why the new standard was developed, to walk you through potential users through the chapters and equations, to alert the users to the optional use of AISI developed Excel spreadsheet and pre-calculated wall tables, and to point out some of the features in the commentary that's provided with the document. And by the way, the document is free for download, as is the Excel spreadsheet. The S250 standard is designed for conventional framing. What does that mean? That means it applies to the standard C-shaped studs or joists and track sections as defined by the AISI standard S240. We do have a minor provision within the S250 document, section B321, on how to deal with proprietary steel framing options. Proprietary being non-standard C-shapes that have different web configurations such as slits, large holes, as well as even roof trusses, which have a completely different design than the C-shape you see on the screen. So why was the standard needed? Well, back in 2014, one of the things that the steel industry recognized that when going through the different model codes, standards, guides, and other material that dealt with energy efficiency, we had accumulated over the last probably 25 years, multiple methods to do the same thing, how to calculate the effects of cold form steel framing in building envelope designs. For example, one of the first energy standards out was just after the oil crisis in 1992, or the 1990s oil embargo, standard 90-75. In there, they use the U factor based method. What's the U factor? Well, you hear by many that U factor is the opposite of R value. That's sort of incorrect. R value is normally material related, such as what is the R value of insulation of a piece of gypsum board, etc. Whereas the U factor normally applies to the entire assembly, not just a single piece of material. However, there were no specific provisions in the envelope assemblies requirements for cold form steel. They merely said your wall had to equal an XU factor depending on what climate zone you were in. Climate zones being like Miami. If you move up to Georgia, you're climate zone 2. If you move up to Chicago, you're climate zone 5. So the higher the number, the colder the region. However, it was left up to the design professional to figure out how to comply. This was frustrating. So by 1995, the Model Energy Code, which was developed by the Council of American Building Officials, which was effectively the 3 US legacy code developers at the time before the International Code Council came around, they introduced the correction factor equations for opaque wall assemblies containing steel framing. The provisions contain both equations and a correction factor table to determine the impact of a piece of cold form steel framing in a wall assembly, and for only wall assemblies. It was also limited only to 16 and 24 inches on center, another barrier that the steel industry has tried to overcome with the new S250 document. Then in 1997, the ASHRAE Handbook of Fundamentals, which is produced by ASHRAE International, which you've also may have all heard about, ASHRAE Standard 90.1, produced by the same people. It's a non-consensus developed guide. However, it's considered one of the Bibles internationally to deal with thermal, moisture, and other subjects. Contains a parallel path and isothermal planes equations for simple light frame construction, such as nominal wood framing. However, in 1997, it introduced what was called the modified zone method, which was created by the Oak Ridge National Laboratory. This became the benchmark now because it was a more exact science on how to calculate the effects of cold form steel framing in building envelopes such as walls. It was extremely accurate. However, it did have its limitations. It was limited to 16 and 24 inches on center, and it could only deal with insulation values in the sense that only if I had insulation in the cavity plus, say, continuous insulation on the outside. So it did have its limitations. Then the International Energy Conservation Code, which was first developed actually in 1997, but the 2000 edition came out with the parallel path correction factor equations, similar to what happened with the Model Energy Code in 1995. In 2003, as a result of the work by AISI, Owens Corning, and Oak Ridge Laboratories, as well as the Department of Energy, we introduced what could be best called as correction factor methods for roofs and floors containing cold form steel framing. The 2004 edition then changed, whereby the calculation methods, fairly simple methods, were replaced with simplified pre-calculation results installed in a table. Why? At that time, from 2003 to 2004, the Department of Energy and other groups wanted to make the International Energy Conservation Code much smaller and easier to use. So it was a usability change, if you will. However, in 2015, we moved back to equations again. Now you can begin to see this buildup of how frustrating it was to keep track of things as well as determine compliance, because the number of methods kept growing. The AISI Thermal Design Guide, while a guide only and not something usable for code adoption, did develop several methods within there to try and, how shall I put it, guide people, if you will, to use that term again, on how to comply the different ways, depending on what jurisdiction you may be in, such as the state of California uses its own homegrown developed method of showing compliance by using simulation tools, whereas other jurisdictions might adopt the International Energy Conservation Code. Or if we go up to Canada, for example, they have the National Research Council of Canada's energy documents that are adopted by the provinces up there. A very good guide, however, again, it had the limitations on how far we had done research, namely for walls, which were primarily 16 and 24 inches on center. And we found that in today's world, people are using different dimensions because of the type of construction going in place for a specific building project, or because of something that's needed to address, say, seismic high wind regions of the United States. So in 2014, the Committee on Framing Standards, which is COFS, approved the proposal to create the new energy standard. The title at that time, North American Standard for Cold Form Steel Framing. However, as you see today, the title is a little different. That's what happens when you have a committee designing things. The scope being that let's produce a document that can effectively address cold form steel framing for walls, for roofs, and if possible, floors in a standardized methodology. The whole idea being, let's produce a standard which can be adopted versus a guide, which we've been doing for years, that can be adopted by a state or province or any other jurisdiction in foreign countries. And let's get rid of all these other methods so that we all work off an even playing field, if you will. So we went through research and development, hiring Morris and Hirschfield, one of the recognized researchers in North America that does thermal analysis. Dr. Merle McBride, retired from Owens Corning, who we had done work for years, as well as the task group members, developed and finally published the document in 2021. So what's the breakdown of the document? Well, its format is similar to the other AISI steel standards in that we have basic chapters that go through administration, general provisions describing what the document will and will not cover. Chapter B, which goes through the three types of atypical C-shaped configurations in design. And we've also added an appendix with pre-calculated wall assemblies, so that rather than doing an equation, one can just look it up. And we modeled that after what some of the codes had done. And finally, a commentary to help describe where to find things, such as the R values for other materials, or specific items about cold form steel to better describe it. We keep the commentary because we want to separate the provisions themselves, the calculation provisions, from the commentary in order that the jurisdiction will be adopting effectively the standard requirements. And as part of the adoption process by most states, they don't want commentary in code. So as long as we separate it, they're happy with that. And their provisions only apply to, for example, Chapter B when they adopt it, but not the commentary. However, the commentary could be used even for a measure when you might have an interesting situation that you have to submit under the alternative means and methods approaches of the adopted code. Chapter B, design. That's just where we'll be going through the entire document here as to how it works. The task group determined that at the beginning there was insufficient test data to support a proposal at this time for floors. Although we had done the research in 2000 for the 2003 IECC, we have a research request to do more there. That's not to say that that calculation procedure from 20 years ago is wrong. We just want to refine it to greater detail so that we're not how shall I put it, overemphasizing the need for insulation, but rather giving a true evaluation for floor assemblies. Walls, there's 3 methods in the chapter. One's called OTZ, and we'll talk about that title in a minute. Method for proprietary steel. This takes a little work, and I'll describe that a little later on the methodology there. And the appendix 1, where we have pre-calculated wall tables for atypical designs, mostly for residential, but for commercial too. And finally, roofs. There are 2 methods there, using conventional steel joists and truss constructions. Now, before I get into the walls method, are there any questions at this time? Do we see any in the chat box?
Not
Oh
yet.
boy, I'm really good today. I'm hot, look out. Okay, we'll start with chapter B, walls, OTZ method. How did we come up with that? Well, we all sat around and thought of an individual name, overall thermal zone. The intent being that is to convey that the focus of our equations is what is the impact of the steel to the entire wall. It is a 3-dimensional effect, unlike many equations that say for wood or other materials which use 1-dimensional type equations. Our equations are based on 3-dimensional analysis, meaning we look at aspects in 3 directions, not just 1. It's 8 basic steps with 12 equations. However, we realized from the beginning, if we're going to get this document recognized and used, we're going to have to make it simple for the general public, as well as design professionals, code officials, contractors, builders, and building owners, if you will. So we designed the methodology such that it only requires simple math, and that all the other hard features like I'll call them coefficients, for example, are already done for you, and you only need to know the basic material types and simple math such as addition, subtraction, multiplication, and division. The method is improved over the modified zone method, which was our closest competitor, if you will, and now includes assemblies with no insulation in the cavities, which we weren't able to do before. Framing members that are anywhere from 3.5 to 12 inches wide at the web. Thicknesses from 33 to 68 mils, which is the thickness of steel. And this is the best part about it, cavity insulation, no cavity insulation, and partial cavity insulation. All advanced features which we could never do before because as I described with the other methods, they were limited to 16 and 24 inches on center and limitations on the thickness of steel. Wall information, what does the user need to know? The wall assembly design, what are you designing for? And that's going to be structurally based mostly. Other impacts to the design may include acoustics, for example. You may be in a jurisdiction where the inside acoustics have to be assessed, and that may impact your design on how much insulation one puts in. You also need to know the list of materials other than steel that will represent the total values of the wall assembly, such as outside sheathing, plywood, OSB, gypsum board. Inside sheathing, what's that going to be? Is it just going to be gypsum board or some other product? The types of insulations you have in mind, the exterior siding, et cetera, et cetera. The other items needed are all provided for you, such as the list of coefficients, conductivity values, and other data concerning steel is presented in tables. So one merely needs to pick the size of the member and then take the numbers that are equated to it in each of the tables. So let's start with a wall type here. What do we see? Well, we see a wall type with exterior air film. We chose a stucco siding. We put on continuous insulation, which we call foam sheathing, gypsum board outside, partial cavity fill with bad insulation. In this case, we're going to use a 2x8 C-shaped member. While not normal in the field, we know that 2x8 4 or 2x6 is more common, but in this case, just to show you how far we can go with this, we also have an airspace in the cavity along with the insulation, which is not unusual in today's market because many of the builders, as well as the owners, in order to be cost effective, want to run, say, the conduits of wiring, of telecommunications, even piping through the outside walls. And if they don't have to muck with the insulation that's installed in order to install their product, that's a better labor saving mechanism, if you will. And then gypsum inside and interior air film. Now be aware, air films are a static number and we provide those for you. However, the other ones, we have to have the designer or owner or builder go out and find the numbers from the manufacturer and use those in the equation. Now you notice here, the OTZ is that area around the stud. Here you can see its total effect three-dimensionally effectively. This is the effective area of how much cold form steel can be affected by the transmission of cold to the heated or conditioned side of a building. So in this case, we chose framing spacing 16 on center, our flange width 1.6 or 1 5/8, web depth 8 inches, base steel thickness 43 mils or 0.0428 inches if you use a ruler, and the conductivity of 495, which is out of one of the tables there. So, excuse me, here we have the basic steel dimensions. Now for the remainder of the materials that make up the assembly, the outside air film, the siding, the continuous insulation, sheathing, cavity insulation depth, we have to know about it. Could be the full depth or half depth or even 0 depth. If there's an airspace, again, that's optional. In this case, we put it in just to show you how it works, as well as the airspace dimension, interior sheathing, and the inside air film. So now we have all our basics. So what are we going to do now? Well, for the national model codes, such as standard 90.1 and the IEC 2024, they've added some additional features that we need to be aware of beyond what the standard currently states. Item A, where steel frame wall contains no cavity insulation and uses continuous insulation, that is the insulation outside of the cavity, to satisfy the U factor maximum in the energy tables or climate zone tables as they're known. The steel frame wall member spacing is to be permitted to be installed any on center spacing. Why? Well, because if I've got my insulation outside, that's effectively demonstrating compliance, and the framing member is not penetrating it in any way, shape, or form, it doesn't matter what my framing spacing is. I just use the outside insulation value. B, where the steel framing wall contains framing at 24 inches on center with a 23% framing factor or 16 inches on center with a 25% framing factor, the next lower framing member spacing input value shall be used. What does that mean? Well, if I'm doing a load-bearing wall condition for my building, such as a house or a small, really up to 9 stories of a cold form steel building, and my walls are load-bearing, I'm probably going to have, depending on the spacing, a 23% or 25% framing factor, just because of the number of members I have to have there structurally. So what do I do? Well, when I use the equation, rather than using a 24-inch on center value to calculate, I go down 1 to 16. And if I have a 16 in my design 16 inches on center, I go down to 12. That's in order to compensate for the amount of framing I'm going to put in structurally for a building. C, where the steel frame wall contains less than 23% framing, example, curtain wall, I can just use the regular values of my equation. So if my framing is at 24 inches on center, I install 24 inches on center in my equation and I'm good to go. Why? Because I have far less framing taking up space in my building envelope wall than I would if I use load-bearing conditions where I have all sorts of stuff to deal with load-bearing conditions such as jack and king studs, headers, sills, etc. With curtain walls, I really don't have much of that. I just have the vertical members, the tracks, and possibly some framing, track framing around the window openings. So far less steel to contend with. So here's our first equation, and I'm sure you're looking at this like you would your taxes. Oh my God, I've got to hire somebody to do it. The answer is no, you don't. If we look at the equation, it is long. However, it's extremely simple. It's only addition and multiplication. Anytime I see the letter C in the equation, I've already got that number chosen from a table. So I've got half my work done already. The other values that I need to know are what is the cavity insulation and what's the continuous insulation, and is there any airspace? And then I can calculate my first equation here, which is determining the overall thermal zone. If you remember that diagram I showed earlier, the impact of the cold form steel framing. And when I talked about all the C values, if you recall, I chose a 16-inch on framing, inch on center framing type, the C-shape designation thickness 43, and they're all my numbers that I need to know to install my equation. That's half of my work done. I move on to my next equation, where I have to determine the framing factor. And there, again, I go up and I know what the mills of my framing member are. I know the flange width, and therefore I can just basically calculate by dividing. Step 3, same thing. I'm in a division equation. Here I'm determining the C-shaped path and its impact. The depth is 6 inches. However, note the insulation is only in contact with the stud that I'm calculating, not the total depth of the framing member. In our case, we chose 8 inches, but only 6 inches is in contact with the framing member web, and that is of the insulation. And just as a reminder, everybody, something when doing cold form steel framing, we need to specify when either putting our specs together or purchasing a product, we need full width bats from the manufacturer, not nominal. Full width, because in steel framing, I also insulate the inside of the steel web of the C-shaped member, not just between framing to framing in the wall. My K value in bullet point number 2 is determined from a slide that comes next. And so by putting those two values in, dividing, I'm done. I get my result of 0.012. I put that in my pocket, keep it for a future equation, and you'll see how that works together as we move on. Step 3, again, there's where I got my, if you see on the far right, my 495, what's called thermal conductivity, or it's also referred to as the K value. My next equation for the cavity path, I'm looking at the thermal resistance of the cavity insulation, the web, etc. And I'm doing, again, a very simple equation, minus or subtraction, division, addition, and I'm done. And I'm now beginning to install some of my values. If you see under the equation FFCS at the top of the bullet, below the where sign, if you will, I'm now pulling in values from other equations and installing them into my equation here. And I will be continuing to do that throughout this in order to figure out what effect cold form steel has. Here, all I'm doing is turning my R value, or U factor that I've gotten so far from the previous equations, into an R value. I now put that into my pocket, and I will use that in a later step. Again, I use the cavity path, and I'm determining the effect of the web airspace. In this case, that 2 inches I mentioned. Again, simple math, subtraction, division, addition. And I'm coming at the net result is a U factor. And here we go with the values I've installed. Now, the 0.91, where did that, we get questions of that all the time for R air. 0.91 comes from ASHRAE International, two resources for that, the Handbook of Fundamentals and ASHRAE Standard 90.1, which had determined through some research that if I have a cavity and the airspace is probably greater than, if I recall, 1/2 inch or the full cavity, I can assign a R value of 0.91 simply because I have an airspace, and that airspace has some insulation value. Not a huge number, mind you, but it does have a value. Again, the web airspace 2 inches, the K value 495 we got from our table, and we come up with a U factor of 7.6. I now move to part 4, or step 4. I'm turning my U factor into an R value. I'm putting that into my pocket because I will use it later. I'm now combining the two R values, simple math, addition in this case. I get the values from two previous sections or their equations, results, if you will. Now I begin to calculate the two paths you saw earlier in our drawing. You'll see it in just a minute. I'm calculating the entire wall now. In this case, air film outside for R sub O. Side exterior is the thermal resistance of the exterior siding. The sheathing, the R value determined from a previous equation. Interior sheathing and the thermal resistance of air film. Again, the air films are a standard value and apply to most any walls. 0.17 for an outside air film and 0.68 for an interior. And here's what we're looking at. I'm looking at the impact of the stud and what happens to it. And if you look to the far right, you see that C-shaped path. It's just what I've described in the previous equation. I'm now putting together all my work into final steps to give me a final value of the impact of not only the steel, but the impact of the wall without steel, and then combining the two at the end. This equation for the cavity path, same as what we saw before, except I'm excluding the steel. And that's all I'm doing here is an addition of all the member components, in this case, siding, insulation outside and inside, air films, the sheathings. And in this case, you see the two arrows. This is where that path was calculated. So I'm up to step 6 now. Finally, step 7 and 8, I'm beginning to finish my work. Again, I'm pulling from the OTZ at the very first equation. I'm putting that value and dividing it by the spacing of the cold form steel framing to show its impact. And finally, my net result here is a case where I'm dealing with subtraction, division, and addition, where I'm taking the two wall types, the impact of the steel and the impact of the wall without steel, combining the two, and my result now is 0.061, which is a U factor number. U factors, by the way, don't have any scalable value, they're just a number. I now compare that to my energy code that I'm complying with. I look in my code and say, if I'm in Memphis, Tennessee, I'm probably in climate zone 3. And if my maximum U factor is 0.070, I've complied. I can now get a permit and put up my building. Now that I'm at the end of this, to staff, do we have any questions up to this point? I know this was a complicated and rapid succession, but let's see if there's anything that's come up for the most complicated part of this document.
Nothing has come up quite yet, but if anything does, I'll be sure to let you know.
Very good. Again, feel free to ask any question whatsoever, and we can try and go back to it and help you with the answer. Okay, other than standard C shape, this was put together for design professionals, but more so for code consultants, specifically those who deal with thermal analysis. Somebody raised the question, okay, I've got proprietary designs. How the heck do I figure this out? Well, what we said was, let's design a formula, has 5 steps, and uses what's called a linear regression curve. Basically, another phrase for it is a curve fit approach, where I use hotbox testing data or other testing data to complete the analysis. In the case of ASTM's 1363, that's the hotbox test that most everybody uses. Oh, that's the appendix already. I'm sorry, I moved too fast. And so what I'm doing in this one is I'm taking 2, 3, 4, or 5, or even more test results, putting them on a graph, seeing how the dots line up, and putting in a curve in order to substantiate how what I interpret the wall will react to thermal transmission from hot to cold or cold to hot, if you will. So in this case, I do need some background and experience to understand research projects and the test data that results out of the research in order to make sure I'm using oranges to oranges to do my comparison. But basically, I'm just putting on a graph data points in order to create a curve and then find where my wall would fit that I'm designing in that curve and use that as the basis for determining what the maximum U factor for that assembly would be. Most people do hire out because the machinery today for calculating this has gotten very sophisticated but simple to use, and it's becoming more widely used and more widely accepted. Now let's move on to the next item. Appendix 1, where I said we had pre-calculated tables. In our Appendix 1, we predetermined what the assembly would be, and this is a cut and paste from that. Basically, framing as shown in the table, flange width at 1 5/8, 43 mils, conductivity 495. Sounds similar to what we did our example with. And then our other construction materials, siding, continuous insulation, exterior sheathing, cavity, etc. So using those values, which are probably the most common that we see, although not exclusive, but nevertheless the more common. We began to put together tables that said, okay, if my framing member is 3.5, 6 inches, or 8 inches, meaning the web, and my cavity insulation is 0 through 25, here's what happens when I add, say, R1, R2, or R3 to the outside of my wall. Here's what the U factor turns out to be. Simple menu approach, like going to a diner. You just sort of choose what kind of wall design you want, and now see if what you want to put on for continuous insulation complies with the code. So if I choose, say, for example, 3.5 inches framing, I have a cavity insulation of 15 batt, let's say, on the inside of that cavity wall, and I'm putting R3 on the outside, you'll see that the value equates to 0.079 U factor. I now look into my code, and as long as I've got a value in the code that's greater than 0.079, I can demonstrate compliance. Now, another feature we put together is a calculation spreadsheet. We got the idea, and some of you may recognize this from the Department of Energy's creation of the ComCheck and ResCheck calculators that most building officials in the United States accept as an alternative method of determining compliance. Well, we've done the same thing here. First, we start off with the information you have to put in to start. This is essential because if you're going to do a calculation, we have this in there so that when you see the results on another page and print it out, the code official can look at it and determine if you followed the rules and demonstrate compliance. In addition, and we've colored the boxes to show you that these are the only boxes you can modify. We put in the shape designation simply as a recording mechanism, but the important features are framing of spacing, designated thickness of the framing, stud depth, flange width, etc. You install the numbers just as I showed how to do the hand calculation method before. And here's some other Additional features, again, the same types of material data that I showed at the beginning. We fill those in, and within seconds, as soon as you click outside the box, you effectively see the following. And that's why you see at the top the name, the date, so you can keep track of what your design is. All the configuration inputs are shown, and the result, which is at the bottom, shows what the net effect is for U factor. You now compare that with the code in effect. And this is a good thing to hand over to the code official who could do the same thing. He could take it and go, okay, give me a few minutes here. And he may have the same calculator. He'll do the same inputs. And if he comes up with the same number, you're good to go. It's also much faster in the sense that, okay, now me as a building owner or design professional or even a contractor can modify it to try and get even better stringency, if you will, depending, and at the same time, depending on what the cost of the project is, to try and come in under budget, if you will, with a better design, such as if somebody was going for a lead project, a GBI Green Globes design or something like that. Now let's start with roofs. This covers only conventional C-shaped only. I can't emphasize enough. However, proprietary designs, by the way, which most roof trusses are, can use these procedures. However, the result will be a more conservative result for the roof assembly than if they hired, say, an energy professional to do a computer model of it, or even doing a test. There are two types of assemblies in this case, conventional and truss type. For conventional, so these are standard C-shaped. It's a pitched roof design, most likely. And all I'm doing is addition, multiplication, and division. Just like the walls of 1995, we're basing this off a correction factor method, meaning if we know our values for the insulations either in the cavity or outside, we merely apply the correction factor to the insulation within the cavity only and assume all other values are free and clear of the deduction that the steel has because they're outside the framing. In this case, we did an example equation here, fairly straightforward. By the way, these equations are also in the spreadsheet for you to use if you want, but quite frankly, that you can do it faster on a hand calculator. Here's the table, the correction factors, and this was all done through research where we know, for example, if I have, let's say, a joist depth of 12 inches, and I have 16-inch on center spacing, that I'm going to take multiply my insulation that's in the cavity of the framing member only, not any other insulation outside the cavity. I'm going to multiply it times 0.27 for our 30 insulation that I might use. So I'm basically taking 30% off of the total value of the insulation, simply because it is being penetrated, or as many people like to use the new term, thermal bridging through the insulation and thus reducing its overall impact. And as I noted before, the same thing we put in the roof calculator as we did for the walls, same calculation sheet, all the green boxes, you fill in the blanks and it produces a value for you in a matter of seconds. Now, something with the truss equations we made a mistake on, and that's a typographical error on our part. However, it's essential you be made aware of it. For roof trusses, we have the same thing. We have correction values in the equations, but in this case, we added 2 parentheses for whatever reason I don't recall, which should not be there, and that's all that warning sign is. But it's the same approach. I install in the RINS location what my value is for insulation, and for a simple truss with no continuous insulation, I simply execute the calculation and I have my number. And here's one of the example equations, if you will. And you can see how much the, without continuous insulation, how much the impact to steel is. Steel does have a great conductivity value. However, it also has great structural capabilities and other benefits. It's just that when we come to energy, steel does a good job of transmitting. Now, if we put continuous insulation on the bottom of our truss, wow, look at the difference here. I install my insulation, in this case R30, in the RINS location, and I get a U factor of 0.03. That's a substantial improvement. Why? Because that continuous insulation provides us a huge benefit of restricting the heat flow through that assembly. And again, we have the same truss calculator in it. However, ignore the do not use. The new calculator took care of that problem you saw earlier. That has been corrected. But the same thing here, I fill in the blank of my general job description, fill in the values in the green space, and it automatically calculates for me. Commentary. We've put several things in the commentary, a discussion about administration, about floor framing discussion, wall framing examples, roof framing general information, and a copy or listing of what the research reports were. And here are some examples of general material information. However, if you are building in a specific jurisdictions, most code officials want to know the real value of, say, the expanded polystyrene or batt insulation, simply because they're all different. For insulation manufacturers, we have to recognize they're competing against each other. So they're going to have different values simply because they're trying to get market share. And that's not good or bad. That's just the way things are. Gypsum board is pretty stable. As are air films, they're pretty standard or static, if you will. They don't change. But just to help you guys along, if you want to use that methodology. For trusses, this is just a example of some of the graphics we have in there to show what's going on. For example, with trusses, we can't have those framing members, meaning the vertical ones and diagonal ones, closer than 4 feet on center. In real life, they're not going to be, they're probably going to be farther apart. Also in real life, they're going to be a proprietary design because there's only 2 major producers in the United States that consume most of the market, and they use a design that doesn't even remotely look like the letter C. And finally, all of our references we use to get where we are today. You can get these online if you do type them in Google. If you really want to read them, they are quite technical, but they're there as a resource in case anybody asks a question. You can simply refer to that. And now it's the end of the program. We're at 1:49. Are there any questions or comments that have come up that we can help these people with?
None have come up, but I
Oh
will
my
keep
God.
that open. I know, you are just so thorough, Jonathan.
I can't encourage people, and here's $20 just to ask something to make me feel better.
Well, one thing I will say is that if anyone has any questions going forward immediately following this, you can shoot an email out to myself. You can reach me at kaylin@metalcon.com. I'm also the contact listed in the Zoom registration form. So if you have questions about AIA certificates or attending certificate or getting your certificate of attendance, we do have a question, Jonathan, that just came through.
Well, before we get to that, just so everybody's aware, I also answer questions. So there's my direct line to my office and my email. Feel free to ask a question about this or anything remotely close to it. And let's go to our question then.
Absolutely. So we have a question from someone who's asking if they want additional information. Where can they look over this PowerPoint or get the materials you have mentioned?
The PowerPoint is something you could distribute if you want,
Okay.
meaning yourself, or they could ask for it from me, I guess. There's no problem there. And the second question was about further information.
Yep, so the formulas that you've mentioned in the presentation.
That's all contained in the document itself. The document is free to download that's a good question. Where do we have it now? Build Steel or something. Let's see if we put it in the front end. We can send that information out to those in attendance. Matter of fact,
Fantastic. So Jonathan,
but it is both, just so everybody's aware, this document we've made free of charge, meaning you only have to register your name. And that's because if we find an error or omission, we want to be able to directly contact you and alert you to it so that you don't continue to do something wrong in future work, if you will. Also, the Excel spreadsheet that I did show is also free of charge. And that's just asking Rose at our office to get a copy and she'll send it directly to you. And if you need help to understand how to operate it, again, give me a call or send me an email.
fantastic. So Jonathan, if you'd be so kind as to send me that information and I can help you distribute that to all of our attendees for today.
Absolutely. There are also many other AISI steel standards, most of which are free of charge. I think we only have one or two now that still require some form of payment, but everything else is at no charge. So you can get the other documents that we may have referred to in our standard just to keep pace with things, if you will.
Amazing. Okay.
Anything else? Any other questions come up?
No other questions have come up since that point in time. So since that is the question that we had to answer, I would love to thank everyone for being here today, for joining us on this MetalCon Live, especially since we're getting so close to the actual show in just a few short weeks. And thank you so much, Jonathan, for joining us today and for presenting and sharing your knowledge. It's been truly appreciated, and we can't wait to have you back for a future MetalCon.
You're absolutely welcome. And again, feel free to send me an email, probably put in the subject line, this was related to your lecture on 9/7, so I remember why you're asking. And we'll help you along to get through the document or even help you understand what the codes may require in a specific jurisdiction.
Perfect. Thank you for that guidance, Jonathan. And again,
good luck,
thanks
everybody.
for yep. Thank you for joining us. Have a great rest of your day. Bye, everyone.